Hi, welcome back to Math 111. Today we're going to talk about Section 1.4, and Section 1.4 is an introduction to functions. You've probably seen functions before. We're going to spend a lot of time with functions this term. This class is called College Algebra, but it really is, we're trying to teach you a different way to think about algebra and mathematics. And one of the ways we do that is by spending a lot more time with functions, because functions and relations, we talked about relations in the last video, are kind of the basics of algebra. What we're doing in algebra is we're taking closer looks at how two quantities will relate to one another. In most cases, we're going to be talking about an x and a y. But this can be anything. It can be the amount of money in your checking account related to how much your bills are. So understanding functions and mathematical relations can really be a pretty powerful thing. So let's get to it. Now, we talked about relations in the last video, and relations are just how one quantity relates to another quantity. And we generally talk about this and when we're doing mathematics, we'll talk about it with pictures because our human brains like pictures. All functions are relations. Not all relations are functions. So a function is, we think of functions as kind of the mathematics or the machines of mathematics. But functions are a special subclass of relations. And what makes them special is the fact that for every x, there is only one y. Or rather, for any x, there is only one y. So let's take a look at these two graphs I've got down here. Relation 1 is just made up of these points, -2, 1, 1, 3, 1, 4, and 3, -1. Now, one of these two graphs represents this relation. Let's see which one is it. This one on the left. We've got the point -2, 1, the point 1, 3, the point 1, 4, and the point 3, -1. So this graph on the left represents relation 1. Let's look at relation 2. This relation is made up of the points -2, 1, 1, 3, 2, 3, 3, -1. That relation is represented by this graph here on the right. One of these relations is a function. The other one is not. Now, let's think about what I said a minute ago. If a relation is a function, then for any x, there will be only one y. Okay, so let's look at our graphs, our relations here. I know that if x is -2, y is going to be 1. Oops. Y is going to be 1. I know, and I'm in relation 1 at the moment. So if I put in -2, I know I'm going to get out 1. We're not going to worry about how I get these things out. We'll get there. Let's look at x is 1. If x is 1, what's y? Ooh, I don't know. Because y can either be 3 or y can be 4. So for an x value of 1, I've got two possible y's. I've got a y of 3 or a y of 4. So this relation here, this one, this top one, relation 1, not a function. Because I don't know what exactly will be an output for an x of 1. Now here's the difference. Let's look at relation 2. If I put in an x of -2, I get out a y of 1. If I put in an x of 1, I get out a y of 3. If I put in an x of 2, I get out a y of 3. If I put in an x of 3, I get out -1. For each and every x in the set, there is only one possible y value. X's are inputs, Y's are outputs. For every single input, there is only one output. Relation 2 is a function. Okay. One way that we talk about checking this is visually with something called the vertical line test. I'm going to go out to Desmos for a minute. And let's just graph our two relations here really quick. So let's graph the relation -2, 1. Whoa. Oh, sorry, we're the new computer. Okay. Someone turned off my num locks. That's no good. That makes me do silly things. 1, 3. So I'm graphing relation 1 right now. And I want to explain to you the vertical line test. So I'm going to pop a vertical line in here too. Remember that vertical lines are x equals some number. And, oh, you should give me a slider. Okay, there we go. So here's the thing. If I can move this vertical line, let me even put this in projector mode so we can see more easily. Okay. And this really isn't a new computer. This is my daughter's computer. She's letting me borrow it for a minute. All right. So if I move this vertical line around, you can see that I'm scooting my vertical line. What I'm looking for is whether or not this vertical line ever anywhere in the x's that are included in the set or in the function. We're going to give that set a special name in a minute. But the x's that are included in the function, if I can go from one end of that x range to another and only ever hit one y, one dot that includes a y, then my function is a relation, or my relation is a function. Let's look at what happened right here. At x equals -1, that vertical line right there hits two y values that are included in the outputs of our relation. That means this relation is not a function. Now let's look at the difference when I look at relation 2. Relation 2 changes this point to a 2, 3. Desmos is occasionally my friend. Sometimes it's not my friend. There we go. Okay. Now what happens if I move my vertical line through all the x values included in the function? Look at that. It never hits any more than one point included in the function. This relation is a function because there's no repeated y's. Okay? All right. So, a set of points in the plane, which is what a graph is, right, represents y as a function of x. If, and only if, that's a mathematical way of saying that, yeah, this is a definition, okay? No 2 points lie on the same vertical line. So what we're saying here is, this graph of a circle, not a function. Because if I pop a vertical line in here and move it around, it hits the graph in two places. This parabola, this partial parabola, that's a function. Because if I drop a vertical line and I move it all around, that vertical line only ever hits the function or the graph in one spot. Only one y for every x. Okay, let's play with these two. Let me see if I can, yeah, I think I can get that graph in. Let's see if I can get S1 graphed in Desmos. I haven't actually figured out its equation before, so let's see if I can do this. We'll keep my vertical line. And this is one of the things you will learn how to do. think it's just that. Maybe not. Yeah, that's pretty close. Okay, now we'll put in a restriction. Give me a sec. I gotta remember Desmos's language. Whoops. There we go. Let's try this. Ha, okay. And we got a couple of points to put on there. We need to put a point at -3/2, comma, -3/2. Oh my goodness. Okay, there's that point. And I need another point. What's that other point? 1, 2. Okay, so the question is this thing, this entire collection of points that I have on my screen here, is this a function? Well, let's check. Let's use our vertical line test with my little orange dotted line here and see. Now I want you to understand everything that's on this screen except for my dotted orange line is part of the relation. Even the dot that's not on the line, that is still part of the relation. So, is this a function? Well, I'm okay so far. I'm moving my vertical line around. I've only hit 1 point so far. Uh-oh. This is not a function. Because right here, when x is 1, I've got 2 possible values for y. This dot and this guy. Yeah, no good. No bueno. Not a function. Everybody understand why? If not, be sure and ask the question when we're together in person. All right, or on forum. Forums are good too. Okay. Let's go back over here. Oh wait, right here. There we go. Now, what about this other one? The only difference between this S1 and S2 is this hole right here. Okay, you see that hole? This guy. That hole means that if x is 1, we're not going to follow this curve. Instead, we're going to jump up to this line, or this point. Let me see if I can make Desmos do this. I don't know if I can. Well, yes, I can. Maybe. It's like putting a hole in my curve. So I could fake it, but I'm not going to. This open circle here means this point is not on my relation. It's not on my graph. Instead, we go up here to this point. Okay, this is a hole. It's a hole. It's a break in the line. It's in the yeah. Okay, so this graph, this S2 represents a function because this guy's a hole. So we don't actually hit a point. on this line at x equals 1. We do hit a point up here. So S1, not a function. S2 is a function. If you're confused by this, ask when we get together. Okay, now we're going to talk about domain and range. And I found a cute little video that I am going to post for you on the Canvas page. It really explains domain and range well. Look for it in the Chapter 1 module, somewhere near equation or section 1.4. There are other videos, but I'm going to put this one up for you. It does a great job of explaining domain and range in terms of a warehouse. So I'm going to kind of use that language. So if we think of functions as whatever goes on in a factory, okay? In factories, we put something in, the machine does something to that, whatever we put in, and we get something else out. Let's say this is a t-shirt factory. Our supply guy goes to the warehouse, gets some fabric, feeds it into our warehouse or into our factory. Our factory does some stuff, and on the outside, on the output end, going into the product warehouse, we have t-shirts. Okay. X's are like the fabric that goes in to the factory. We give that, and we can only put certain things into that factory, right? We can only put fabric in. If we try to go get cement blocks, our function's not going to work. We're not going to get t-shirts out. It's going to break our machine, right? We call the things that we are allowed to put into a function the domain. The supply warehouse, the stuff in the supply warehouse, that's the domain of our factory. So the X's that we can put into our function are the domain of the function. What comes out, the Y's, are called the range. So for the factory we're talking about, the range is t-shirts, because I said this is a t-shirt factory, right? Mathematically, for mathematical functions, the range is the set of all Y's that we get out after we do whatever we're going to do to our X's. So X's are the domain, Y's are the range. Let's look at an example here. This is a relation given to us in roster notation. The domain is the set of the X's. So the domain is the set -3, 0, 4, 5. Okay? The range is the set of Y's. 2, 1, 2, 2. Now, don't let the repeated Y's upset you. That's okay. This is domain and range are only defined for functions, by the way. We can have repeated Y's. We cannot have repeated X's in functions. So here it all is in glory. For this set, the domain is the set of all X's. 3, 0, 4, 5. The range is the set of all Y's. 2, 1, 2, 2, or the way we would actually write that is just in brackets 2, 1, because these are not ordered. Okay? When we give roster notation, we tend not to repeat repeated values. So we would just give the list 1, 2 as the range of this function. So when we write down the domain and the range, we can't necessarily recreate the function from that list. These don't have to be in this order. Okay? What we're doing is we're just writing down all of the X's and all of the Y's. Now, we won't usually do these things in roster notation, but roster notation is a nice way to introduce the concept. We'll usually look at either equations or graphs, or equations and their graphs. Equations are also functions. It's another way. So equations with two variables are relations. Many of them are functions. Some of them are functions. Okay, so if we want to find the domain and the range of this graph, let's talk about it. So we always start at the biggest and go to the smallest. So let's talk about the domain first. The domain, remember I said, was the set of all x's that are included in the graph. So let's look at this. We see here that our graph, our picture of our set of points, starts at 1 on the x-axis and keeps going down. All right. PowerPoint is not being nice to me. There we go. Right? So my domain, now, so there's a hole, and this is an open circle. And this open circle means that the x equals 1 is not actually included in the domain. So the domain is the set of all x's, put a domain, that are less than 1. Now in set builder notation, sometimes you'll see this, but we're just going to go for set of all x less than 1. Or remember we talk about interval notation. And interval notation just lists the endpoints of the set, of the range. So and it always goes smallest value. In this case, that's going to be negative infinity to largest value. And your symbols tell you whether or not the value is included. These two things both say x less than 1. Again, if interval notation confuses you, be sure and ask when we get together. Okay. Think about this. Maybe look in your textbook, make sure you understand but the domain, the key here, I want you to not get lost in the weeds. I want us to remember what we're talking about. We're talking about the domain. And the domain came from the x's that I'm allowed to put into this function. If I pick up an x that's bigger than 1, I don't know what to do with it. Because my picture of my relation, my curve here, this curve, right? It doesn't have any instructions for what to do with an x bigger than 1. It's like bringing cement blocks to my t-shirt factory. I don't know what to do with those. Okay? Now let's talk about range. Range is related to the y's. So we talk about the y-axis. We can see that, sorry, okay, this will do. We can, no, I don't really want that. Go away. Go away. Highlighter, green. My y's start at 4 and go down. There's no way I can get an output that is bigger than 4. I can't get glassware out of my t-shirt factory, right? So my range, our y's less than, now this time, see I have 4 is included, so it's less than or equal to 4. Or in interval notation, that's going to be, whoops, 4 is my biggest value. My smallest value, not what I want, then, is negative infinity. And my biggest value is 4, but 4 is included, so I use a square bracket. Okay. Remember the domain is the x's, the range are the y's. Okay. And this is just the exact same thing we just talked about, but all written out for you. All functions are relations in math world, but not all relations are functions. So when we talk about equations, they may or may not describe y as a function of x. We use a special designation that is an algebraic representation of functions. And this is possibly the most important way to view them. So we're going to talk about how we figure out if an equation represents a function. And it's the equation of a relation, if that represents a function. It's not as hard as you think it's going to be. So let's talk about this. What we do is we solve the equation for y. All right? So if we look at this one, but we have to make sure we're getting the whole solution. So the top one, if we solve it for y, we go through the steps I've got shown here. And when we get to this step right here, this one, where we've isolated the y squared and now we're going to take the root, we remember we need to take the positive and negative root. That's a huge clue. If you have to take a positive and negative root, this relation is not going to be a function. Let's take a look at the graph of this relation on Desmos. Let's get rid of this, and this, and this. And we've got x to the third plus y squared equals 1, x to the third plus y squared equals 1. This is the graph of that relation, and you can see it fails the vertical line test. So this relation is not a function. And our algebra told us this because we had to take the positive and negative root. Okay. Let's look at x squared plus y to the third equals 1. Again, we're going to isolate y. This is how we're going to test to see if a relation represents a function. Isolate the y to the third, take the cubed root, and we get y equals the cubed root of 1 minus x squared. We didn't have to take a positive and negative root. There's no question. There's only one root. This relation is a function. It does represent y as a function of x. And if we take a look at this guy on Desmos, x squared plus y to the third, we'll see, sure enough, it passes the vertical line test. And this relation is indeed a function. And we knew that algebraically because there was no question here when we were able to solve for y without having to use any sort of an absolute value or a plus or a minus or anything funky. We could just solve for y. Okay. What about this one? X squared y equals 1 minus 3y. Again, we're going to solve this for y. We're going to isolate the y, so pull all of our y's to the left-hand side, factor out the y, and then divide by x squared plus 3. And we get y equals 1 over x squared plus 3. No tricks. This is a function. So let's take a look at the graph. X squared times y equals 1 minus 3y. Whoops, y. It's not a very exciting graph, but it is a graph. It is a function. Now, just to convince you that we solved this correctly, let's take a look at the graph of y equals 1 divided by x squared plus 3. Hey, looky, they're the same. So we did our algebra right. So Desmos can also help you verify your algebra, right? You can put in your original and what you think is the y equals only solution, and use it to verify your algebra. If you solved an equation correctly for y, or for x for that matter, the two graphs should lie right on top of one another. So here's a way to check your work while you're doing your homework. But the point here is we were able to solve this relation. We were able to solve it for y. We put y in terms of x with no messiness. And so that means that this relation is indeed a function, and the graph verifies that. This passes the vertical line test. All right. That, I believe, is it for today. It is. So I encourage you to work on the homework, and we will get together in person soon for a talk so you can get your questions answered. In the meantime, be sure and post any questions you have on the forums. I will talk to you again soon.